Okay, good morning, good afternoon, good evening. Welcome to our lesson. And in today's lesson, we'll be talking about the concept of mathematical induction. I'll be talking about the concept of mathematical induction. I'm sure we are familiar from the topic with the topic mathematical induction. So this is what we are going to have. Okay, sorry. Okay, here we go. So, and this topic, mathematical induction, is simply a topic in MA 110. Those in the School of Mathematics, those in the School of Mines, yeah, those are taking MA 110 mathematical methods. So we're looking at the mathematical induction. So mathematical induction, first thing is first, we'll define what the mathematical induction is. So we are simply saying that mathematical induction is the process. The mathematical induction is the process of proving a general theorem. Proving a general theorem or formula. So in this concept, we'll be looking at proving various theorems or various formulas if at all they exist, or if at all they indeed are real, or they can be used in various expressions. So mathematical induction is a process of proving a general theorem or a formula, and in short, we'll be proving this involving positive integers. So we're trying to prove various formulas here, various theorems using positive integers. So by positive integers, what are we trying to insinuate? Or we're trying to usually use the values where n can be equal to 1, n can be equal to 2, n can be equal to 3, n can be equal to 4, and the values continue to count in that manner. So we understand that positive integers are simply positive whole numbers. So 1, 2, 3, 4, and etc. etc. So we'll be using the mathematical induction. This is just a process which we're going to be using in the proving of general theorems. So there are those general theorems which we know in mathematics, and there are those general formulas which we know in mathematics. So would you grab those formulas and prove them if at all they are real, and they can be satisfied and be embraced too for certain positive integers. That's what we are trying to use mathematical induction. So I want you to understand that in this process of mathematical induction, there are only two steps. There are two distinct steps. We're going to look at two distinct steps in the proof. So whatever you're going to be doing, the only major proofs you're going to be using as you are proving any of these general formulas according to mathematical induction, you are going to be using two distinct steps. And the first step which we are going to be using is step number 1. We're going to be using the base step. So every time we are trying to prove this mathematical induction, you're trying to prove these formulas by mathematical induction. Number 1, try to prove with the first step, which are going to be the base step. So in the base step, what is going to be happening in the base step? Here, you're just going to show by actual. You can show by actual substitution that the proposed theorem or formula is true for n equal to 1. The base, remember, trying to prove this concept using positive numbers, and from the base, the first value of n we're going to be using is n. So every time we look at the base step, we're just trying to substitute in the formula for n equal to 1. Is it true? Is the formula satisfied when I have n equal to 1? That is the base step. So where n in this case are basically the natural numbers. So we are trying to show by actual substitution that the proposed theorem or formula is true for n equal to 1. So if it is true for n equal to 1, it means that when we insert in that theorem, obviously we're going to have p of 1. Let's say if the theorem is p of n. So in there we insert 1 in the function, and then we will conclude that is this true? Is this yielding? Is this being satisfied? If this is being satisfied, we will check as our first step that the base step is satisfied. So in the process of the mathematical induction proof, we will have to do the first step, which are going to the base step, where in the base step you just do an actual substitution of the n equal to 1 and conclude that p1 is indeed true for the theorem or the formula given. That's what you're going to do. The next part or the next step of the proof is you proving the step we are simply calling to be the inductive step. You're just going to show the inductive step. And in the inductive step, what are you supposed to do? In this step, it is just an issue of you assume that the theorem or the formula is true for, so you're trying to assume that the theorem or the formula is true for n equal to k. So it's an assumption. Assuming it means you already know that this theorem, if I put any n equal to k, where this n is a natural number case, so we assume that for n equal to k, this theorem is true, or this formula is true. Then prove that it is true for n equals to k plus 1. So this is an assumption which you are going to be making. If the formula is true when we replace n with k, then our goal will be to prove that that theorem or formula will also be true this time around for n equal to k plus 1. This is the inductive step we are going to be using. So in the inductive step, which we are going to be using here, if this is true, assuming that this is true, and then we prove that for n equal to k plus 1 it is also true, we will conclude that that formula is indeed true for all values of n, which are natural numbers. So with these two steps, you can go ahead and conclude that the theorem, sorry, my handwriting today, that the theorem is true for all n in the natural number set, because remember, natural number set are just positive whole numbers. So step number 1 is the base step. you substitute in the proposed theorem n equal to 1 and show that it is true. Step number 2, you check for the inductive step. In the inductive step, what do? You assume that it is true for n equal to 1. It's just an assumption. Then what do? You prove that it is true. It is true for n equal to k plus 1. Once this is done, conclude that the theorem is indeed satisfied for all n in the natural number set. That's the mathematical induction. So we'll look at various proofs in mathematical induction, various questions, and so forth. So we'll have to look at the first example there. So let's look at the first example. So we can look at the first example, example 1. So in this example, we are going to say prove. So this is example 1. We are going to say prove that 1 plus 2 plus 3 plus the count continues until I reach n is equal to n open bracket n plus 1 closed over 2. I want us to prove this formula. So what is the formula here which we have? The formula is n open bracket n plus 1 over 2. Prove that this formula is satisfied. It is correct for this series. Remember, this is a series, and the series is basically a summation of a sequence. So we are trying to sum up various terms until the nth term. So if I'm trying to sum up this, it is just as good as using a certain general formula which can be satisfied there. And that general formula, we're replacing it with this guy. So the question is, we want to prove that this formula is indeed true for this series, for this sequence. We want to check, is it true, this formula true for this sequence which we have here and for this series which we have there. That's what we want to check. So we are trying to prove by mathematical induction. So remember, we are proving by mathematical induction. We shall prove by mathematical induction. And mathematical induction only has how many steps? 2 steps. We shall prove by mathematical induction. Mathematical induction only has 2 steps. Step number 1 in this mathematical induction is the base step. Is the base step. And the base step, we know that in the base step, we're just trying to confirm in the formula for n equal to what? N equal to 1. That's what we're trying to check. So in the formula given, check if it is true for n equal to 1. That's the base step. So you start checking and counter checking. You tell yourself, okay, for n equal to 1, what are you going to have? Remember, when n equal to 1, it means I am in the first position. What is in the left hand side? From the formula is 1 plus 2 plus 3 plus the count continues up to plus n to be equal to n open bracket n, according to the question, n or what? N plus 1, n plus 1 over 2. This is the formula. So we want to check for n equal to 1. What is happening when our first position in n is equal to 1? What is going to happen? That's the goal. So when n is equal to 1, what are we going to have? The left hand side, this is A1, this is A2, this is A3 until I reach AN. So when n is equal to 1, it means I am looking at the first position there. So what is going to happen? The first position, obviously the left hand side will just be equal to a 1, because this is just the first value. So I just going to have the first value. So n equal to 1 will make me have the first term. which is 1. So maybe when n is equals to 2, we're going to have 1 plus 2. When n is equals to 3, we're going to have 1 plus 2 plus 3, which we are going to have. So in the base step here, it means we're just testing for the first position, first value which is going to be obtained. What is going to happen? We're trying to assume that the natural number n, or the position where we are standing at, it is the first position. That is why the left hand side will just concentrate on the value of 1. So for this base step to be satisfied, we are simply saying that the left hand side I'm going to have a 1. It means on the right hand side where the formula is, if we insert n with 1, the answer should be equal to this 1, which we are going to have. That's what we say. So we're now trying to check from the right hand side. The right hand side is what? We're trying to substitute 1 in the formula. So if we have 1 at n, so now look at this. Maybe let me start with the formula. The formula is n plus 1 over 2. So it means for n equal to 1, this becomes 1, open bracket 1 plus 1 close over 2. So it means that if we simplify this, we're going to have 1 multiplied by 2 over 2. And this is 2 times 2, and 2 divided by 2 is equal to a what? A 1. So what are we simply seeing here? We are seeing that by default, the left hand side is equal to the right hand side. So if the left hand side is equal to the right hand side, what is the left hand side having when n is equal to 1? When n equal to 1, the left hand side is equal to 1. The right hand side, when n is equal to 1, the right hand side will be equal to 1. So we can see that for n equal to 2, equal to 1, the formula is true. We can see that the formula is true for n equal to 1. So here in the base step, we just prove for n equal to 1. So now look at this. If let's say we just wanted to just continue proving in ascending orders of n, maybe let's say we check, let n equal to 2. What is going to happen in the left hand side when n is equals to 2? When n is equals to 2, we are going to have a1 plus a2, meaning we're talking about 1 plus 2, which is going to give us a 3. This will be a left hand side. This will be the left hand side. So when n equal to 2, it means I'm in the second position. It means I'm adding the first two terms, a1 plus a2, and a1 is 1, a2 is the 2 from the sequence. So number, we're trying to check the right hand side. The right hand side is our formula n plus 1 closed over 2. So if n is equal to 2, this means I'm going to have 2 multiplied by 2 plus 1 over 2. 2 and the 2 can go, will divide, and the answer will be equal to a 3. This formula is still true when n is equal to 2. So sometimes if you wish to do things further, you can also check the second step, or maybe the second value of n. So the best step is just you understanding to prove the formula for n equal to 1. That's what you're trying to prove. So n equal to 1, you prove that formula if it is satisfied. You can even try to go further and just to confirm your allegations, to say, what about for n equal to 2? Can it be satisfied? Remember, you're trying to prove the formula is indeed true for all values of n. You're trying to check maybe for n equal to 2. For n equal to 2, you are seeing that the left hand side is just as good as a1 plus a2. And a1 plus a2 is, a1 is 1, a2 is 2. So if I sum up the 2, I have a 3. Right hand side, the formula is n plus 1 over 2. So n plus 1 over 2 over 2. This means I'll have a 3 on my right hand side. The left hand side is equal to right hand side. So with this allegation here, we are simply saying that for n equal to 2, the formula is true. The formula is true. Now remember, you cannot just conclude that the formula is true for all values of n. That is why we are simply saying that for conclusion to be made, once this passes, the base step passes, you can go ahead and now check for the inductive step. We go to step number 2. Step number 2 is the inductive step. The inductive step. And in the inductive step here, what are we going to say? We are going to assume let me do this. Okay, so we are on step number 2 now. So on step number 2, what are we going to do? We are going to assume for some. Remember, inductive is just a matter of assumption that n is equal to k. So for some integer n equal to k, that's the assumption. So if n is equal to k, what is going to happen? We are inserting in the system n to be k. So it means nk, we're talking about something to do with 1 plus 2 plus 3 plus, the count continues until I reach what? Until I reach k. So if n is equal to k, it means after the n, we're inserting what? K. So this will just be equal to the right hand side. Instead of me having n, the formula, remember n is now represented by k. So the formula will now be k, open bracket, k plus 1 over 2. Don't forget, we are talking about the sequence. We're talking about the sequence, which is 1 plus 2 plus 3 plus, the count continues until we reach n, which was given by the formula n plus 1 over 2. So we're trying to prove that this formula is correct. So using the inductive step, we're trying to assume that let n be equal to k. Then we're going to have 1 plus 2 plus 3 plus up to n, which is now n is equal to k, will end at k here, will be equal to n is now k plus 1 over 2. So this is an assumption which we are making here. This is an assumption. So assuming that the formula is true for n equal to k. So assuming for some integer n equal to k, the formula is true. You can even say the formula is true. Remember, this is the assumption. So assuming that this formula is true, what are we going to have? In this system, we are replacing upper the n to be k, and we'll have this system of expression. So what do? You keep this as your first equation. Equation 1. Remember, this is an assumption that this formula is correct when n is equal to k. So number, what does the inductive step says? If n equal to k, it is correct. Your goal, it is now to show that it is also true for n equals to k plus 1. So keep this. So the next part is we want to show that it is true for n equals to k plus 1. That is your goal. Once you've shown this, it means you can even conclude that the formula is correct for all positive values of n. So if n is equal to k plus 1, what are we simply saying? Which one is big between k and k plus 1? Obviously it is k, isn't it? And k plus 1 dead. So it means in the first place, we had the summation from 1 up to k. But this time around, we've exceeded further from k. K is just k. But the next term after k, obviously it will be k plus 1. It will be smaller than k plus 1. That's what we're trying to assume here. So that is why we are simply saying that we are now trying to sum up all the values from 1 plus 2 plus 3 plus up to plus. Instead of n is equal to k plus 1, it will now be k plus 1. And this is equal to, the formula was n, open bracket, n plus 1. Upper the n, it is k plus 1. This is the value of n. Upper the n, it is k plus 1. This is k plus 1. But this is the value of n, but in the formula it is plus 1 over 2. Remember the formula? The formula, it is n open bracket n plus 1. So this n, it is now k plus 1. This n, it is now k plus 1. This is what we're simply saying. We're trying to show that the formula will also be true when we replace n to be k plus 1. So it means what we're now going to have will be something like 1 plus 2 plus 3 plus up to we reach k plus 1 to be equals to k plus 1. Obviously here we have like terms. 1 plus 1 is what? We know that it is 2. So I'm going to have k plus 2 over the 2. And we can take this to be our what? Our second equation. So we have equation 1 where we made an assumption for n equal to k, and equation 2 which we want to show for that it is true that for n equals to k plus 1. We are okay? So number, what are we going to do to achieve our claims? What are we going to do to achieve our claims? So we'll try by all means to use equation 1 so that we can get equation 2. Because this is more like a higher value of n which we have. So to the smaller value of n, k, we would grab this and we'll do something to it so that we can come up with the equation number 2. So once we do something to equation 1, once we do something to this equation 1, and we later on come up with equation 2, we can indeed show that to this equation we are able to have this equation for the next value of n, because this is more like a previous value before I reach k plus 1. So using equation 1 now, so we have two equations here. Equation 1 with an assumption that n equal to k is true, and we are trying to show that nk plus 1 is also true. So to show this, we are going to need help from equation 1. So what are we saying here? We are simply saying by induction, equation 1 can be used to get equation 2. So how is this possible? This can only be possible by adding k plus 1 on both sides of 1. I'm sure mathematically we know that this is true. By adding both sides of 1. So for this to be true, if I'm summing up k values 1 plus 2 plus 3 plus until I reach k, so for me to get equation 2, it means the left hand side here, if I am at k, the next value I'm going to sum up will be a k plus 1 value. So it is satisfied. I'm going to reach this value of k plus 1. But remember, for this equation 1 to be satisfied, whatever I do to the left hand side, I also do to the right hand side. So I have plus k. Since I want number for values of n which are reaching a k plus 1, to the left hand side I'm going to add k plus 1. Even to the right hand side I'm going to add k plus 1. So this is what is going to happen. So it means that I'm going to have 1 plus 2 plus 3 plus, the count continues until we reach k. This was in the first equation. But to get k plus 1, it means we'll continue and add k plus 1 to it. So that this becomes, in the first equation, what did I have? I had k plus 1 over 2. So to it, since in the left hand side we added the k plus 1, even on the right hand side I'm going to add a k plus what? Plus 1. Then we'll simplify this expression so that we can be able to get equation 2. So let's work with the right hand side. The right hand side, what is going to happen? We can simplify this as a single fraction. Simplify this as a single fraction. Lowest common denominator, that's a 2. 1 times that, this is k, open brackets, k plus 1. This is more like over 1. So 2 times that, this will be positive 2, open bracket, k plus 1. So that when we break down everything, what are we going to have? This is just as good as when you expand this, I'm going to have k squared plus k. When I break this, I'm going to have plus 2k plus 2 over 2. So that when you simplify everything on top, we're now going to have k squared plus 3k plus a 2 over 2. This is a quadratic expression. Remember, the left hand side, it's still continuous the way it is. 1 plus 2 plus 3 plus k plus k plus 1. 1 plus 2 plus 3 plus, the count continues, k plus 1. 1 plus 2 plus 3 plus, the count continues up to k plus 1. So number, what is my numerator? The numerator is k squared plus 3k. K squared plus 3k over that. I believe this can be factorized. Huh? This is quadratic expression. Two numbers multiplied to give you a 2. When you add them, you give you a 3. Tell 1 and each one. So this becomes k squared plus, this is 2k. Actually, I'm even going from the kind. I could have even factorized it in the first place. Plus what? Plus k plus 2 over, we're going to have what? Yeah, this is over 2. Implying that we can factorize, this will be k, open bracket, k plus 2 plus 1 there, open bracket, k plus 2 when we factorize this. So that when we continue, we're now going to have k plus 1 and k plus 2 over the 2 expression there. So if this is achieved, what am I going to have? Remember, the left hand side is still 1 plus 2 plus 3 plus k plus k plus 1. And what has been achieved here? This is what? Still our equation 2, which is equal to equation 2. So we have used equation 1 to show that it is equal to equation 2. Remember what equation 2 was? Equation 2 was this guy. K plus 1 over k plus 2 over 2 on the right hand side. And we have seen that if we make an assumption that n equal to k, it is true in that equation, it means that we are able to show that the equation or the formula can also be true when n is equal to k plus 1. So what can you conclude? Conclude that the formula n plus 1 over 2 is true for n equal to k plus 1 when n is equal to k. Hence, it is true for all natural numbers, for all n in the natural number set. Remember, talking about positive values for n. So that will now be true for all values of n which are positive, and you are done. So mathematical induction, remember, is the process by proving, of which you can prove a mathematical theorem, a mathematical formula, that it is satisfied for positive values of n. That's what you are saying there. So the same thing we can do here will also happen for another example I can show here. I think I will show you another example here. Let's go to example 2. So example 2 here, I would want us to prove that 1 squared plus 2 squared plus 3 squared plus the count continues until I reach n squared. This is true, or it is equal to the formula n plus 1 it is equal to yeah. So this will be equal to n plus 1 open bracket 2n plus 1 closed over 6. Prove that this formula is true for this series. So we want to prove that that is true. The same step. What are we doing? We are proving. Proof by mathematical induction. That's what we are doing there. The proof, how do you even spell proof? Proof is by mathematical induction. So we said that there are how many steps in mathematical induction? 2 steps. Step number 1, we show the base step. The base step is for n equal to 1. For n equal to 1, we have the left hand side to be equals to 1 squared, which is just by default equal to 1. And then what are we going to have on the right hand side? And then the right hand side will replace n with 1 in the formula. Means I'm going to have 1 plus 1 open bracket 2 multiplied by 1 plus 1 closed over 6. So this becomes, this is 2, so I'm going to have 2 times 1 there, and this will be a 2 open bracket 2 plus 1 there, and this is a 3 over 6. So this is just as good as 6 over 6, which is equals to a 1. So the left hand side, so we can see that the base step is true. So next, what are we trying to check there? We're now going to check the inductive step. If you wish to, you can even sometimes confirm for n equal to 2. We said we can also confirm for n equal to 2 if you wish to. When n is equal to 2, what is your left hand side? Your left hand side will be 1 squared plus 2 squared. That's the second item we are adding. So this is just as good as 1 plus what? Plus 4, which is going to give us a 5. And what about the right hand side? The right hand side is just as good as what? Having the formula there, when n is equal to 2, this will be 2 multiplied by 2 plus 1 closed multiplied by 2 multiplied by 2 plus 1. I'm just replacing n with 2 in the formula over 6. So this becomes 2 multiplied by 3 multiplied by 4 plus 1, that's 5, if I'm mistaken, over 6. So this 6 and this 6 can go, and we'll have a 5 there. As simple as that. So for n equal to 2, the formula, it is true. So it is true for n equal to 2. Next, what are we going to do number? We're now going to prove the inductive step. What does the inductive step mean? We're going to assume n equal to k. What is going to happen? We're now going to have 1 squared plus 2 squared plus 3 squared plus the count continues. Instead of n squared, we're now going to have what? Since n is equals to k, we're going to have k squared. the right hand side, instead of n formula having n values in a variable n, we're now going to have k, since n is equals to k. So we're going to have k, open bracket, k plus 1, open bracket 2k plus 1 over 6. This is our first equation from the assumption. So we're assuming that n is equal to k. What does the inductive step say is, if we assume this, we have to show that it is true for n equals to k plus 1. So we need to show it is also true for n equals to k plus 1. We need to show that it is also true for n equals to k plus 1. So what is going to happen there? We're going to have 1 squared plus 2 squared plus 3 squared plus the count continues until we reach k plus 1 squared. And this formula will now be equal to, upper the n, it is k plus 1. Open bracket, upper the n, it is k plus 1. Plus 1. Upper the n, it is k plus 1, this will be 2 k plus 1 plus 1 over 6. Simplifying that further, what am I going to have? I'm just going to have, this will be equals to k plus 1. The second one, these are like terms, this is a 2, k plus 2. The second one, we can break down this will be 2k, and this will be 2, and then 2 plus 1, it will be a 3. That is why I'm going to have 2k plus a 3 there. This is over what? Over 6. So it means that with the n equal to k plus 1, we have the summation formula to be equal to k plus 1 squared to be equal to this, and we'll keep this as our second equation. That's what we're going to do. Now, since this was an expression for up to k, and this is an expression up to k plus 1, we will use equation 1. We'll use equation 1 to get equation 2. So to equation 1, we're going to add k plus 1, since it will be the next term after k, so that we are able to obtain from this, we'll be able to obtain that. That will be our goal. So we start. So what are we saying here? We're saying from equation 1, we add k plus 1 squared, since this will be the second term number after k. So we add k plus 1 term. I don't know what has happened here. From equation 1, we add k plus 1 term, so that we have, so if that is done, what are we going to have? We're now going to have 1 squared plus 2 squared plus 3 squared plus the count continues until I reach k squared, but to this I'm going to add the next term, which we are going to call k plus 1 squared. So from equation 1, we just ended at k squared, and the next term after k is k plus 1. That is why it will be plus k plus 1 squared. It means on the right hand side, the first equation was just k plus 1, 2k plus 1 over 6. This was the term up to k, but since we are adding k plus 1 squared on both sides, this should now be plus k plus 1 squared on both sides. That's what we're going to have. So with this done, what will be our duty now? Our duty is to break this down and simplify it further. So simplifying this further, we can simplify the single fraction. The lowest common denominator is 6. 6 into 6 is 1. 1 times the numerator, I'm going to have what? This is just as good as k k plus 1, 2k plus 1, close. This into this is 6 times 6 into that. We're going to have, 6 times that, we're going to have 6 multiplied by k plus 1 squared. This is what we have. Now, we can do something here. Mathematics is all about having big eyes sometimes. So now look at the numerator. The numerator, this is more like the first term and this is second term. We can factorize the numerator there. What are we saying? We are seeing k plus 1 as a common factor there. So it means k plus 1 can be factored out. So I can have k plus 1 being factored out. So it means if this is factored out, what am I going to remain with? Here, I'll just remain with k, open brackets, 2k plus 1. Actually, this is a 2k here. 2k plus 1. And then here, since k plus 1 has come out, we'll remain with just 1k. 1k plus 1. That is what I'm going to have. Plus 6k plus 1, which is remaining when we factor out that. This is just the numerator which has been factored out. But remember, the denominator, it is still over what? Over 6. So when we simplify things number up, what am I going to have? We are now going to have k plus 1 as a factor there, and this other factor, this will be what? We can simply break that down to be 2k squared plus k. We can expand this to be plus 6k plus 6 over 6. So that this continues and become k plus 1, 2k squared plus 7k plus 6. Though we're taking it back again, sorry. Anyway, so if that is the case, we can even factorize. That is a quadratic function. We can factorize it number in pairs. So factorizing it in pairs, this will just be as good as if this is k plus 1, it's already a factor. But inside here, what is going to happen? In fact, you could have just factorized from the start here. So when you factorize this quadratic function here, what am I going to have? We're going to have two numbers. When you multiply them, they'll give you a 12. When you add them, they'll give you a 7. We're going back to the first case here, if you look at it very well. So in the first case here, we have, am I correct? This is 6 and 1, 6 by 1. So we're going to have, if we break that down, we're now going to have, so we're going to have 2k squared plus 4k plus 3k, because the two numbers, when you add them, they'll give you a 7, it's 4 and 3. When you multiply, they'll give you a 12, that's 4 and 3. So 4k plus 3k plus 6, this is what I have there, over 6, and this can now be equal to k plus 1, open brackets, we can factor out the k there, so that we remain with k plus 4. We can factor out the 3 there, so that we remain with k plus 3. Okay, plus 2, sorry. And that done, what am I going to have next? I'm now going to have over 6. Then the factors now will be, the first one is k plus 1. The second one will be this k plus 4. The third one will be, wait a minute. This is 2k as a common factor. Let's go back to this. What is common between 2k squared and 4k? What is common is a 2k. So 2k will be outside, then this will become a 2 here. So it means the first common factor there, this will be 2k plus 3. So you can have 2k there plus 3. And then we'll have k plus 2 as another common factor. K plus 2. as a fact, and this will be over 6, as simple as that. And this is what our equation 2 had, if you look at it very well. So if you go back to equation 2, you'll find that equation 2 was written as k plus 1, k plus 2, and 2k plus 3 as our equation 2 over 6. So it means we have achieved our goal, where 1 squared plus 2 squared plus 3 squared up to plus k squared plus k plus 1 squared, it will give us this, which is equation 2. Thus, we are simply saying that the formula n, what was the formula? The formula was n plus 1, 2n plus 1 over 6 is true for all values of n which are positive, as simple as that. So we have achieved our goal in proving that this formula is indeed correct. That's what we have there. So this was in concepts of trying to prove certain summations and so forth. So we are trying to use what? The mathematical induction there. So what were we using? We were using the mathematical induction. So the first task I'm going to give you there is, so you can submit this homework, kapani task, kapani homework, kapani exercise. So the task I'm going to give, you can submit this on our WhatsApp. So I want you to prove, use mathematical induction, prove that Sn is equal to 5n n plus 1 over 2 for an equals to 5n. So I want you to prove that one. So number, a leakage on how you are supposed to prove this one. Number 1, a leakage on how you are supposed to prove this one. Number 1, the an, remember these are sequences and series. So if I give you a formula Sn, you know that this is a summation formula. If I give you a formula an, this is an nth term formula. So it means an here is what is going to give you values on each term. Yes, if an is equals to 5n, it means you are able to come up with the terms. You are able to come up with the terms from an formula. So when n is equal to 1, this means that a1 will be equals to what? Upper the n wabika for 1, yalaba nshinga ni 5. When n is equal to 2, upper the n apa wabika for 2, it means a2 yalaba nshinga, it's 10. When n is equals to 3, upper the n apa you put a 3, and it implies that a3 will now be equal to what? A3 will now be equals to 15, because the sequence should be in the form of A1, A2, A3, and the listing continues. Now, these are the listing values, so it means that the sequence will have something like 5, 10, 15, and the list continues. But we're not talking about, we're not concerned in the list, we're talking about proving this formula here. This is a series. It means we are summing up. So since we are summing up, we are trying to sum up these terms. So the concept is we are trying to prove that 5 plus 10 plus 15 plus until you reach what? N. Until you reach maybe something like 5n, not n, but 5n, because the formula is an is equals to 5n. So 5 plus 10 plus 15 plus until you reach this expression 5n. The formula should be equal to, the formula given there is what? 5n, open bracket, n plus 1 close over 2. This is what you are trying to prove there. So in most cases, sometimes what are you going to do? They'll just tell you to say, can you prove this? Without giving you this information. They know to say you're able to come up with the information from the process of an. Because an is a sequence. So you develop your sequence yourself from positive values of n. So when n is 1, when n is 2, when n is 3, maybe that's 3 values. And then when you sum these up values up to what? Up to the formula 5n. This should be equal to the left hand side. The right hand side, the formula given there. That's what you are being taught. So this is the task I'm giving you. So I want you to prove this formula. It means you know the steps. Number 1, you check the base step. When n is equal to 1, check the left hand side and the right hand side. And you check, maybe you can even confirm when n is equal to 2. So when n is equal to 1, the answer should be 5 on both sides. When n is equal to 3, the answer should be 10 plus 5, which is 15 on both sides. You can even confirm on that one. And then after that, you prove the inductive step. So only 2 questions I'm giving you. So you prove the first one, of which I've already given you the educate on how to break it down. And then the second one I want you to prove is, this is to prove that Sn is equal to n plus 1 for an equals to 1 over n plus 1. This is another formula there. So it means you can come up with your sequence first and sum all those values to be equal to the say Sn. So you can even start with the best step. The best step is going to come up with a sequence. So this is how your question is going to come. But how do you break it down? Start with coming up with a sequence first. The sequence will be A1, A2, A3, and the count continues. It means when you are talking about this formula is going to be A1 plus, A2 plus, A3 plus, until you reach plus that over n plus 1, until you reach this, and this will be equal to the formula which are going to be n plus 1. That's what I've been taught. So when you're finding a1 here, what is a1? A1 is going to be formed from here when n is equal to 1. So when you press 1, 1, 1, so this would be more like 1 plus 1 multiplied by that. So it means obviously the first term will be 1 over 2. If we are talking about the second term, n is equal to 2. 2 plus 1, that's a 3. 3 plus times 2. So this will be more like something like 1 over n is equal to 2. So you're going to have 2 plus 1. So this will be 3 multiplied by 2, which is a 6. We're going to have something like 1 over 6. So the count will continue until you reach n plus 1 to be equal to n plus 1. So I've already given you a leakage there, how to break it, the first step. So show that the formula is true from mathematical induction. So base step when n is equal to 1. Inductive step assuming that n is equal to k then show that it is true for n equal to k plus 1. That's what you're going to do. Otherwise, thank you very much. We'll see you in the next lesson. Send your solutions. Send your solutions to our contact WhatsApp 0964 736805. Mr. Sot. Thank you very much and have a blessed day.